Okay, good evening, good morning. It's February 23. The time is around 12:30 in the morning. Okay, I will try to check my calendar. Oh, it's fine. Okay, my next lesson on my channel will be lesson number 12 on advanced mathematics. Okay, let's proceed. This is advanced mathematics lesson number 12. The main topic is series RLC energized by a direct current. It's a direct current circuit. Okay. So we are having a problem. The given problem is something like this. The connection of the three components are actually series, and the components are actually resistance, inductance, and capacitance energized by a direct current source. That's why our topic for tonight is a series RLC DC circuit. And the problem here, the main problem is actually to find current as a function of time. Lesson number 12 will be a little bit complicated compared to the other past two lessons, because under lesson number 12 there will be three cases. Okay, let's proceed. To find for current as a function of time with the given circuit RLC connected in series energized by DC, we will take the summation of voltages. Upon closing the switch, we try to take the summation of the voltages. Okay? The summation of voltages, and they should be equal to 0. Sigma notation, capital letter B, they should be equal to 0, meaning the summation of voltages around this closed loop here should be equal to 0. We will start with the power source, plus E minus IR minus L di dt minus 1 over IC, the integral of I dt, and this should be equal to 0. This is plus, it's a voltage source. The voltage, the drop across the resistance is actually a voltage drop, so this is minus. The voltage drop across the inductance is also a voltage drop. This should be a negative L di dt. And the voltage across the capacitance, it's a voltage drop, so this should be negative again. And as was discussed from the previous discussion, lesson number 11, the voltage across the capacitor is 1 over C, the integral of I dt. And this should be equal to 0. So if we transpose all the negative terms to the right, what will come out will be E equal to IR plus L di dt plus 1 over IC, the integral of I dt. Okay? We are now given this equation here. It involves differential and integral. So to find current as a function of time, we must have to eliminate this integral sign over here. So to eliminate the integral sign, we will take the differential of all the terms. Okay? The differential of E is 0. E is constant. And the differential of IR, R is constant, I is variable, so the differential of IR should be R di. Okay? The differential of L di dt, it will be L is constant. Di dt is just the rate of change of current with respect to time. So if we take again the differential, what will come out will be L. This di now will become square. So this is d square I over just simply dt. Okay? Plus 1 over C. The differential of the integral of I dt, okay, will just be simply 1 over C times I dt. Because if we try to take the differential of the integral of I dt, this should just be simply I dt. Okay? Differential, integral, they will try to cancel out. So upon taking the differential of this, the simplification will just be simply 1 over C the times I dt. Okay? Simplifying this one, we will multiply all the terms by the value 1 over L times dt. So the first one here times this, we'll go first for this second derivative. This L here will disappear, right? And this dt here goes with this, so dt now will be dt squared. So the second term multiplied by 1 over L dt, what will come out is actually d square I over dt squared. Dt now will be squared because a dt times dt will be a dt squared. Okay. What's next? This is the integral RDI times 1 over L dt. What will come out will be the ratio R over L. Okay. Di, we multiply that by 1 over dt, it will be, there will be a dt underneath. So the next term will be R over L times di over dt plus the last part will be, what will come out? This dt here will disappear, right? It will cancel with this. What will come out will just be simply the product of LC underneath. 1 over C times 1 over L is actually 1 over LC. This is multiplied by I. So this is multiplied by I. And this should be equal to 0. So after taking the differential and multiplying all the terms by 1 over L dt, what comes out is actually a homogeneous second order differential equation. Why homogeneous? The right hand side is equal to 0. We are now given the second order homogeneous differential equation, that is d square I over dt squared plus the ratio R over L times di over dt plus 1 over LC times I, and this should be equal to 0. For the meantime, compare this I to y and this t here to bx. And since the involved variables are actually I and t, it should be d square I over dt squared plus the ratio R over L times di over dt plus 1 over LC times I, and this should be equal to 0. So for the solution of this, we will be starting with the solution I equal to k e raised to mt. We have passed by that, what you call this principle, right? Complementary solution. I will check my camera again. Taking the derivative of I prime will be km e to mt. Taking the derivative of the first derivative, what will come out will be the second derivative. I double prime now will be km square e raised to mt. So we will take the value I prime, and the value I double prime. We put it on the homogeneous second order differential equation back here. Okay. I prime is di dt, and I double prime is d square I over dt square, right? So substituting, first one will be km square e raised to mt plus the ratio R over R times km e to the mt. We are following this, plus 1 over LC times I, which is k e raised to mt, and this should be equal to 0. Okay, let's try to simplify. There is a common factor k e raised to mt, so we will multiply all the terms by 1 over k e raised to mt. So the first one multiplied by this k here will disappear, e raised to mt will disappear. What comes out for the first term after the multiplication will just be simply m squared. For the second part, this term here multiplied by this k here will disappear. E raised to mt will disappear. What remains will just be simply the product. This is m, right? The product of R over L times m. So the second part, after multiplying by 1 over k e to the mt, the result will be just be simply the ratio R over L times m. R over L times m. The last part, we will multiply this one by this one will vanish, right? So what remains on the third part will just be simply the ratio 1 over LC, and this should be equal to 0. And we call this one the so-called characteristic equation. Okay? It's a quadratic equation. The coefficient of the square term is 1. The coefficient of the linear term is actually B is actually R over L, and the pure constant term is 1 over LC. L is constant, C is constant, the product of two constants will be constant, so 1 over constant is still be constant, so C is actually a pure constant, and the value is actually 1 over LC. So if we try to compute for the value of M, I think we could not factor out this one by inspection, so we will be using the so-called quadratic formula. The quadratic formula is actually M equal to negative B plus or minus the square root of B squared minus 4AC over 2A. Substituting values for A, B, and C back here. Okay? And if we try to simplify this one, it is just an algebraic manipulation, guys. This is B is actually negative R over L plus or minus the square root of R over L quantity square, that is B, minus 4 times 1 times C, capital letter C. Okay, that is 1 over LC. This C here is different from this. This is the C constant and this is the capacitance of the capacitor. Okay, and if we try to simplify this one, this is all over 2 times 1. And if we try to expand the resulting, what do you call this, right-hand side, we distribute this 2 here. So minus R over L divided by 2 will be negative R over 2L. And then this 2 here, we put it inside the radical. So if we put it inside the radical, what will come out? There will be, we put it inside the radical. 4 over 2L. It will become R over L. Okay. There will be a 4 here. So I will make this as 2L. Then I will just square that one. And for the second part, this is minus 4 over LC. But we bring inside the 4, right? So there will be a 4 here. So this 4 here cancel with this. So what comes out inside will just be simply the ratio square root of R over 2L quantity square minus the ratio 1 over LC. No more 4 here because the 4 cancels. Okay? And the value now will be alpha will be minus R over 2L, and beta, the second part, is actually the square root of R over 2L quantity square minus 1 over LC. Okay, on this one. Okay, let's bring out the 3 cases now. For the 3 cases, it will be something like this. If the value inside the square root, case number 1, if the ratio R over 2L quantity square is greater than the ratio 1 over LC, okay, the circuit is said to be so-called under overdamped. Overdamped meaning it will not oscillate. Oscillate, maybe the graph is something like this. Okay, so I place it here under case number 1. If the ratio R over 2L quantity square is greater than 1 over LC, the circuit is overdamped. It will not resonate. Where M1 will be alpha plus beta, M2 will be alpha minus beta. They are real and unequal. Okay? For case number 1, if this is greater, what will come out will be, the roots will be real and unequal. So the solution of the current now will be this. That is I equal to K1 A raised to M1 times time plus K2 times E raised to M2, which is alpha minus beta T. Alpha minus beta times time. This is now current as a function of time for case number 1. And the circuit is overdamped, meaning it will not oscillate. For case number 2, if the ratio R over 2L quantity square is equal to 1, the ratio 1 over LC, we could say that the circuit is critically damped. Critically, it will not oscillate. Okay? So, if D are equal, the value inside the radical will become 0. This one. If these two here are equal, they should be, they will cancel out. So, it will be, beta will be 0. And M1 is equal to M2. It will just be simply equal to the first part, alpha. And they are real and equal. Okay? And the equation of the current now for the critically damped circuit under case number 2 will be K1 plus K2T closed quantity times E raised to alpha T. No more beta because beta is 0 because the ratio R over 2L quantity square is equal to 1 over LC. Beta is 0. So this will be the current now as a function of time for case number 2. That is for critically damped circuit. Critically damped, critically it will not oscillate. For case number 3, this is the worst case scenario. If the ratio R over 2L quantity square is less than, the first part is greater, right? Case 1. Case 2 is equal. Case 3, if the ratio R over 2L quantity square is less than 1 over LC, the circuit now is said to be oscillatory circuit. The graph will be something like this. It will oscillate. Okay? So if we try to compute for beta, beta will be the ratio R over 2L quantity square minus 1 over LC. But if 1 over LC, okay, is less than R over 2L quantity square, we will try to factor out. We will bring out negative 1 over here times open bracket 1 over LC minus the ratio R over 2L quantity square. Minus 1 times 1 over LC is this one. Okay? And minus 1 times minus R over 2L quantity square is the first one. We just rearrange. Then we will try to replace minus 1 by the value G square. So what comes out inside will be a G square times 1 over LC minus the ratio R over 2L quantity square. Right? Taking the square root of both sides, the square root of G square will be plus or minus J, and the square root of the remaining term inside will just be simply the square root of 1 over LC minus the ratio R over 2L quantity square. For the meantime, we do not know the value of this, so we will just place the square root as it is. So M1 now will be alpha plus J beta. There is a J here now, meaning the circuit is, what do you call this, it's a complex thing. It got a real part and the so-called imaginary part because there is a J thing here. And M2 is actually alpha minus J beta. We see this one, they are both, we call them the so-called complex conjugates. Why complex conjugates? The real part are the same, the imaginary part are the same except for the sign on the second part. That's why it's complex conjugates. And the current now as a function of time for oscillatory circuit under case number 3. It's a little bit complicated. I think we have passed by this one. That is I equal to E raised to alpha T times the quantity C1 cosine of beta T plus C2 sine of beta T. This is now current as a function of time for case number 3. That's it, guys. Okay, so you now know the variations of lesson number 12. It could either fall under case number 1, case number 2, or case number 3. Case number 1, when the ratio R over 2L quantity square is greater than 1 over LC, the circuit is overdamped circuit. And this will be the equation of the current. For case number 2, for a repetition, before we go tonight, this morning, the ratio R over 2L quantity square is equal. The first one is greater, right? The second one, they are equal. And for the third one, the ratio R over 12 quantity square is listen. So for case number 1, it is overdone. Case number 2 is critically done. Case number 3, it is an oscillatory circuit. The graph will be, there's an oscillation. It's a, what they call this, it's a complex wave. Okay, that's it guys. Okay, this is lesson number 12, an application to series RLC energized by a direct current source. Okay, so for those who are studying what they call this advanced mathematics in relation to circuitry, this is for you guys. Please click like, and if you want to subscribe to my channel is at actually youtube.com/@proofdavidj.delasres. Okay, I got a long videos on differential calculus, integral calculus, differential equation, and this is now the third long video for advanced mathematics, and I am now on lesson number 12. Okay, good morning Los Angeles.